I'm Neil Clark, and this is the second part of the series of talks discussing the characteristic direction, a geometrical approach to differential gene expression. So at the end of the previous talk, I gave a broad description of what I mean by the characteristic direction. Here I'm just going to go into a little bit more detail about the exact calculations that we perform when we're calculating the characteristic direction. So in the figure on the right, we again have our two-dimensional gene expression space, and we have the red and the blue points which are indicating microarray profiles from the two states. Now what we're going to do is we're going to use linear discriminant analysis, which starts by writing the conditional probability that the class is red or blue, conditioned on the gene expression profile. Now, what we can do is we can define a variable, we'll call it g, and g can take on two values, red or blue, as it describes the class. And we'll also define another variable x, which describes the gene expression profile. Then you can use Bayes' probability to write an expression for the conditional probability of g conditioned on x. So this is the probability that the class is red or blue, conditioned on the gene expression profile. And this is written as in terms of the class conditional density and the prior probability. So the prior probability is written here as pi sub k, which is the prior probability that the class has value k, where k can be red or blue. And we have the class conditional density, which is the probability density of the gene expression values conditioned on the class. So k. The next thing we do in linear discriminant analysis is we model. We have a simplified model for what the probability distribution for the gene expression values are conditioned on the class. And the model is a simple one in that it's a multivariate normal distribution, which means that the distribution can be characterized completely in terms of its mean, indicated here as the Greek letter mu, and a covariance matrix, which is written by sigma. And so we can write the class conditional density as an equation in those variables. Given that we have a model for the class conditional density, we can then estimate the probabilities. Given the gene expression profile, we can estimate the probability that the profile came from a red or a blue state. So I don't need to go into the details of these equations, it's just to give you an illustration of how these calculations are done. And the upshot of it all is that we can divide the space into two. Gene expression profiles that sit in the red part are more likely to come from the red biological state, and gene expression profiles in the blue part are more likely to have come from the blue biological state. And this division is a linear boundary, a hyperplane, which has an orientation completely characterized by one direction, illustrated in the figure here with the arrow and the letter B. And this B is a vector which describes a direction in expression space, and it's written purely in terms of the covariance matrix and the mean vectors. So we don't need to go into too much detail about these calculations. It's just to illustrate the kinds of operations that we do when we calculate this direction. The final thing we're going to want to do once we've calculated the direction is then to interpret it in terms of the genes at the gene level. The way we do this is we use a high-dimensional version of Pythagoras' theorem. Now the total differential expression, illustrated here with the letter m, can be expressed as the square of m can be expressed as the sum of the squares of all the components of the characteristic direction vector, then you can interpret the contribution to M from any given component is the square of that component. So essentially what we're saying is the more aligned the characteristic direction is with an axis corresponding to a given gene, the more significant that gene is in the differential expression. The final thing we want to address is the curse of dimensionality. Now, we've seen that our calculation of the characteristic direction depends on calculation of the covariance matrix. This is a very large matrix when we have a very large number of genes, as it has a number of dimensions. It's a matrix, a square matrix, which has a number of columns and rows equal to the number of genes in the genome. So we're estimating a lot of covariance parameters based on only a few samples. So we expect to have lots of errors in our estimate of the covariance matrix. So what we do is we use a process called regularization or shrinkage, in which we essentially apply a smoothing filter to the covariance matrix. We try to smooth away the errors while retaining the signal. And this is done very simply by replacing the covariance matrix with a mixture of our estimated covariance matrix with a diagonal matrix. So, and the balance between the two is controlled with a parameter which I've called here gamma. A value of gamma equal to 1 means that we have the mixture is completely weighted towards our original covariance matrix, and a value of 0 means that we've completely sphered the data and replaced it with a diagonal matrix. Intermediate values mean that there has been some intermediate level of smoothing. So this completes our description of the characteristic direction method. Next we're going to validate the method, and we're going to try and compare it to other commonly used approaches to differential gene expression.